All right. So we're going to get into Chapter 7 now. You got a brief taste of Chapter 7 in the lab activity that we did on Tuesday with water gems. You know, the calculations it was doing, that's Chapter 7 stuff. Because finally in Chapter 7, we're setting aside all of our silly assumptions about there being inviscid fluids in the universe. Of course there aren't inviscid fluids. Every fluid has viscosity. And so finally in Chapter 7, we're going to start to classify the energy losses that arise when you have a fluid with viscosity. So that's what you were doing in with the water gems assignment. That report will be due on Tuesday, December 2nd. And I use the word report with air quotes because all you're submitting there is the screenshots and then the explanation that I asked for each of the conditions where you're explaining what happened and why. So bring that on Tuesday, December 2nd. Tuesday, December 2nd is going to be a little weird. And here's why. There are like 180 international students at Marshall who are enrolled in like a 6-week academic English course. The majority of them are from Mexico, but there are also some from Saudi Arabia. And on the 2nd of December, those students who are just at Marshall for like 6 weeks are going to learn a little bit more about the College of Information Technology and Engineering. So in the morning, they're going to have like a PowerPoint and a lecture. And then in the afternoon, they're going to come over to the engineering building. So it is going to be like wall-to-wall international students on Tuesday the 2nd. They're bringing 180 students to this building in addition to however many are normally here. And so some of them are going to be back in the lab. And in fact, starting at 1 o'clock, I'm going to be giving them like the song and dance about how great hydraulics is, and here's the hydraulic jump. And so they'll be back in the lab like they're breaking it up into groups. And so simultaneous to our lab at 2 o'clock that day, there's also going to be a group of international students who are going to be like watching you do your lab, right? So I'll be telling them about what lab you're doing as you're doing it. It's going to be with the pipe rack. That's the lab that we're doing on Tuesday the 2nd. So you've used the pressure gauges before. You know how all that works. I guess the pressure will be not to tip the pipe rack over when you've got a bunch of, when you're under the microscope of both your professor and all of these international students. So Tuesday is going to be weird. You've got a homework assignment due, that lab submission, and then we'll do another lab back in the lab area that day. So thus far, let's take a look at what we've been thinking about fluids. We've been thinking about the pressure of fluid, the effect of gravity, the effect of shear stress. All of those are mechanical forces. But now, with the energy principles that are in Chapter 7 and the energy equation, there's just one big equation that you'll learn in Chapter 7. It allows you to start doing calculations like how much energy is required to move fluids from place to place. So you can start doing calculations related to pumps. The effects of pipe friction enable you to estimate what the pressure loss is going to be as water flows through a pipeline. And when there is a physical scenario that is governed by gravity flow, for example, a tank connected to another tank, but the water level is lower, and here's a pipe connecting the two, without the energy equation, you wouldn't know how quickly the water is transferred from the big tank to the lower tank. But when we start to look at how much friction is there in that conduit, then you can do the calculation of how quickly is the water transferring from one place to another. And then also, there are these things called local losses, and that's what we're going to do in the lab next Tuesday. And I showed you on the pipe rack that when you have a pipe that is making a gradual transition, there's going to be less energy loss as the water flows around a nice gradual bend like that than when it's like a sharp 90-degree angle and the water's having to make that turn rapidly. It induces a lot of turbulence. There's a bigger pressure loss because that turbulence causes a loss of energy. So we'll be able to account for obstacles, bends, valves, and compare different types of valves. If you go over to the hardware store, you'll notice that there are ball valves, gate valves, lots of different ways of stopping the water from flowing through a pipe. And we'll take a look at that in the lab and notice the effect of energy losses. So here was Bernoulli's equation, and let's just compare it to the energy equation that you're using in Chapter 7 because they look deceptively similar. But in Bernoulli's equation, we had some assumptions that we had to make when we were applying it. If you ever had, in the near future, a situation where you had to answer a question, like a conceptual question, and it was, what are the 4 assumptions behind the use of Bernoulli's equation, what would you write? What are the 4 assumptions when you're using Bernoulli's equation? Okay, steady flow, meaning that the flow rate is not changing with respect to time. Inviscid fluid, meaning that this is some magical fluid that doesn't have any viscosity, because the reason why we say that is that Bernoulli's equation doesn't account for energy losses, and it's only an inviscid fluid that won't have energy losses between one point and another. Okay, so steady flow, inviscid fluid, there are 2 more. Incompressible, so it's again this magical fluid that can't be compressed, and on the spectrum of feasibility, liquids are a lot more incompressible than gases, even though we apply Bernoulli's equation to both, liquids and gases. What was the last assumption? No? Along a streamline, that's right. So that if we had, Bernoulli's equation we'd sometimes use for a nozzle. Here's our nozzle, and the Bernoulli's equation is the kind of thing that tells us when you've got a slow velocity, then it goes to a fast velocity, how does the pressure change from location 1 to location 2? So what we said with the streamline thing is that, the water is flowing through here, and it sort of follows a typical pattern, and you can only apply it along the same streamline. Otherwise, Bernoulli's equation isn't valid. So those are 4 things that kind of tied our hands and created situations where if we applied Bernoulli's equation along a pipe where the 2 points are too far apart, then we're going to get into trouble with the inviscid assumption, because when the 2 points are far apart, then you're going to start seeing energy losses. Or if we were using a gas for Bernoulli's equation instead of a liquid, then we get into trouble with the incompressible assumption, because gases are compressible. If we wanted to apply Bernoulli's equation on 2 different locations in the flow field that aren't connected by a streamline, then we've deviated from the assumptions and we're going to get inaccurate results. So here's the answer to all of our problems, the energy equation. And it looks similar. It has so many of the same terms, but we've added in a few other ones to account for the times when we can't honor those assumptions. So let's go through what are those instances. How does it compare? There's a pressure head term. That's the same. Alpha 1 is different from alpha 1, and then there's a line above the V. We've seen that line above the V before. Does anybody remember what it meant? Average velocity. Exactly, that's right. And so instead of saying with Bernoulli's equation, when we said V, we meant V right here at a single location, like the instantaneous location-specific velocity. In energy equation, we're going to say we're applying it not at a point, we're applying it at like a cross-section. And so when we say V1, we mean the average velocity everywhere across that area. So that's why the bar is there, average velocity. Alpha is a kinetic energy correction factor. And I've got a slide that goes into more details about that in just a minute. We'll talk about the kinetic energy correction factor. Z1 is the same, Z1, Z1. H sub P is a pump head term. And we will apply the energy equation between 2 points in a system. And it can be applied between any 2 points in a system. It doesn't matter where. Let's just say, for example, that we've got 2 tanks. And the water is flowing from tank 1 towards tank 2. this, since it's clear, well, maybe it's not clear, but the water level at 2 is higher. So the only way we can get the water to flow from 1 to 2 is by putting in a pump here. And you'll notice that the pump head term, H sub P, it means pump head, it's on the left-hand side of the equation. In this case, it's important that we always have 1 be the upstream location and 2 is the downstream location. And so, put that in the margins there, that 1 is upstream and 2 is downstream. This equation is direction dependent in a way that Bernoulli's equation wasn't direction dependent because you had the same stuff on both sides of the equation. Here, you don't. The pump head term is on the left side of the equation. So what it's saying is that if you're calculating how much energy is there between 1 and 2, because the energy equation calculates energy, the amount of energy that there is at 1 is equal to the amount of energy there is at 2, but you account also for the pump head that is being added. A pump adds energy. We'll talk about how it does that. It does it a little bit differently than you might first think. But a pump adds energy, and so that's why we put it on the left-hand side of the equation. These other two terms take away energy, and that's why they're on the right side of the equation. So we've got, again, the pressure at 2. Here's the pressure head term, the velocity head term, the elevation term. But now H sub T, T stands for turbine. In the same way that P stands for pump, they are either adding or subtracting energy, and as expressed in these terms, it has units of length. So pump head is how many meters of energy is being added. We express the energy in terms of a height. That seems weird, but it's not weird, so don't say it's weird. It's like, pressure can be expressed in terms of a height as well. If we've got some delta H like this, pressure usually we expressed in terms of pascals or newtons per meter, but we can also express pressure in terms of just how many meters of water is there above that location. And so in the same way that we sometimes express pressure as a height, we can express energy as a height. And so the pump head, basically, it's like boosting the water. When we express it as a height, we're saying this pump is adding enough energy to the system that it's like it lifted the water in a way. So when we say the pump adds 10 meters of head, it's like equivalent to if this pump had lifted the water up an additional 10 meters. So in that way, it kind of makes sense, right? Turbines take away energy, and H sub L stands for head loss. And here's a really important thing that you need to add in the margins here. H sub L has two terms. It has two components. H sub L is head loss, and there are two things that cause head loss. There's H sub F, which is frictional losses, and then there's H naught, which is local losses. And sometimes local losses are pejoratively referred to as minor losses. But you're going to give local losses a Napoleon complex if you call them minor losses. Make them think that they don't matter. They're called minor losses because in comparison to frictional losses, usually local losses are much smaller. Like if you've got water flowing through a pipeline, most of the energy is going to be lost due to pipe friction. And the amount of energy that's lost because of a couple of bends and a few valves, that's a much smaller fraction of how much energy loss there is. But there are some situations where actually the local losses exceed the frictional losses. So, any questions so far about the energy equation? All right, we already talked about how V bar means average velocity. H sub P is the pump head. H sub T is the head given up to a turbine. H sub L is the head loss, and it has those two components. Alpha is the kinetic energy correction factor, and so the kinetic energy correction factor varies based on what the velocity is through the pipe. And here you can see, this is the Trans-Alaskan Pipeline. It carries oil from Prudhoe Bay to, I don't know, somewhere else in Alaska. It's a really long pipeline, and the interesting thing, one of many interesting things about this pipeline is that at the same time it can be carrying different substances. Like they may have gasoline going through this section of the pipeline, and behind it will be oil, and the two things don't mix because there's a special lining that tries to keep the flow fairly laminar, so there's not a lot of mixing turbulence, and so they're able to have like different plugs of flow going through there of different substances. Here is a velocity distribution, a velocity profile showing laminar flow. When you've got laminar conditions, then the flow at the center of the pipe is the Vmax. The velocity is double the average velocity. And in a case like that, then the kinetic energy correction factor will be 2.0 if you have laminar conditions. But what you'll remember is when we were back in the lab playing with the apparatus with the plastic view tube, laminar flow is pretty rare. Most of the time, flow isn't laminar. And so we're not going to have alpha equals 2 very often. The way that you calculate alpha is actually you integrate the ratio of the actual velocity at a single point to the average velocity. And so that's what this is. This is integrating over the entire radial area of the pipe. If you look at the velocity here relative to the average velocity, and then you make another incremental area, and you find the average velocity for that area relative to the average velocity. If you go through the process of integrating those ratio of the velocities, then that's where you come up with alpha. And the long story short is that for laminar flow, alpha is 2, and turbulent flow, which is 99.99% of the time in a municipal network, you're going to have turbulent flow, then what we use for alpha is 1.05. And 1.05 is close enough to 1 that unless we're trying to be super precise, most of the time we don't even bother with alpha. I mean, I need to tell you about it so that you're aware that, you know, this is the real this is the real energy equation. But for many of the examples I'll show you, and your homework assignments as well, unless it specifically tells you to account for alpha or gives you the alpha that you should incorporate in your calculations, you can just neglect it. You can just assume that 1.05 is close enough to 1. All right, well, let's do an example. Oh, I didn't bring in my notes today. I'll have to go grab them after I set this up. We've got 2 tanks that are connected by a pipe, and we have a little bit of information about that pipe. We know that it's 300 millimeter diameter pipe. We've got the water surface elevation for the 2 pipes. So let me modify this one that I've already got here. We've got no pump or turbine between 1 and 2. The water surface elevation here is 200. So the Z1 is 200 meters. And Z2, I'll make it a little bit lower. Z2 is 190 meters. And let's see. Water's flowing from tank 1 to tank 2. The length of the pipe, so length is 200 meters. And then the diameter of the pipe is 350 millimeters. And we're given an equation here that defines the head loss. We're given the equation that head loss can be calculated as 0.04 LV squared divided by 2G. All right. We're going to spend a lot of time in next semester's hydraulic engineering class actually finding ways to calculate the head loss due to pipe friction. And like the golden standard for that, as I've already told you about, is the Darcy-Weisbach equation. You know, that's the one when you first start up water gems, you have to switch it from Hazen-Williams over to Darcy-Weisbach. And Darcy-Weisbach says that head loss due to pipe friction is FLV squared divided by D2G. This is the Darcy-Weisbach. Equation. And I'm writing it right now, not because you need to know it for this class, but because I just love it so much I can't resist. FLV squared divided by D2G. Here, in this example, I'm lumping a couple of terms together and just saying, assume 0.04. So I'm lumping together the F term and the D term together, and I'm assigning just by default 0.04. But this equation that is given is saying that the amount of energy loss that is going to happen depends on the length of the pipe and the velocity of the pipe. And so let's think about that in practical terms. If the pipe is long, if it was 400 meters instead of 200 meters, then you're going to have double the head loss. And so that makes sense that the longer the pipe, the more frictional resistance there's going to be. And you'll lose energy between the 2 points more if the pipe is longer. In the same way, the velocity is going to have an effect on the energy loss. And this is a little bit less obvious than the case of the length. So why is it you think, why will a higher velocity lead to more energy loss as water flows through the pipe? Why is it that, you know, here it is, here's our conduit, and the water's flowing through there. How come doubling the velocity, in fact, because it's velocity squared, if you double the velocity, you're going to have 4 times the energy loss. Why does a faster velocity mean more energy loss? Why would it matter if the water's moving fast versus moving slow through the pipe? More frictional resistance, but why? Why is it dependent on velocity? It's a tough one. It is more frictional resistance. It's related to the turbulence, because you can think of it as the pipe is sticky. It's not really sticky, but the pipe is sticky. It's like trying to hold on to the water. It doesn't want the water to move through there. And so at the edge of the pipe where the water is touching the pipe, the faster it's moving, the more the pipe is holding on to it, and it's also causing turbulence in there. Remember, turbulent flow, as turbulent flow goes up, so does the energy loss associated with the turbulent flow. So this is basically conceptually saying the longer the pipe, the more head loss you'll have. The higher velocity leads to higher energy losses. And so we want to find out how fast is the water going to go through this system when we have the conditions that are specified. One other thing I want to ask you about is, why do you think I've selected, you know, if this energy equation can be applied at any 2 points in the system, you know, I could have made this be 1 and this be 2. Or I could have said, let's have this be 1 and this be 2. And it will work. You know, the energy equation is valid between any 2 points in the system as long as they're connected by water. From like a strategy standpoint, why do you think I picked the top of the water surface to be my locations 1 and 2? All right, the pressure is 0 because this is air above it, and so it's going to simplify my calculations. I'm going to be able to cancel out the pressure head term, and I also know the elevations there, so the z term is known. And the other thing that's great is there's no velocity at location 1 or location 2. I mean, the water level's falling a little bit, but you know, you've done problems having to do with how quickly tanks empty, like 1 centimeter per second. You know, the velocities are so low, the velocity's going down here as this tank empties, and it's going up a little bit here as that tank fills. But these tanks are so huge that we can assume the velocities are 0. So, like, what's canceling out? The pressure head term is 0. The velocity head term is 0. We're given the elevation. There's no pump. The pressure at 2 is 0. There's no velocity at 2. We know the elevation. There's no turbine. So the only thing that's left is this head loss term. So in other words, the energy equation is simplifying down. Just because we were smart about location 1 and location 2, it turns into this. Z1 is equal to Z2 plus the head loss. And we know that the head loss term is 0.04 LV squared divided by 2G. Now I just need to give you one more warning and then I'll ask you to start doing some calculations. And that warning is this, and this will come up lots of times. So if you just get it straight in your mind now, then it'll never be an issue. You'll never lose any points. There's 3 different velocities that are described in this equation. There's velocity 1, which means the velocity at location 1. And we said that here at location 1 there's no velocity because it's falling so low it's negligible. Same thing about 2. But you look at it and you say, well, I only see 2 velocities. There's this one and that one. But no, the other velocity is embedded in the head loss term. There's also a v in here because the head loss is dependent on the velocity in that formula. So what v is this? Is this the velocity at 1? Is it the velocity at 2? Some other velocity? It's what? It's the velocity in the pipe, right. So it is how quickly the water is moving through the pipe. That's the velocity that you use in the head loss term. Okay, so I'm going to pause for a moment and I'd like you to tell me what is the flow rate through the pipe, volumetric flow rate, cubic meters per second in the situation that's described. So here is the energy equation. Once we cancel out all the terms that don't apply, you'll be able to solve for the velocity and then from that velocity find Q. Of course, it's fine to collaborate on this one. Okay, so the difference in elevation between the 2 points is what's driving the flow. You know, the bigger the difference in elevation, the faster the velocity. It's the driving force that causes this movement through the pipe. So with the 10-meter deflection between the reservoir on the left and the reservoir on the right, then we just have Z1 minus Z2 is 10 meters, then the 0.04, 200 meters for the length, V squared is our unknown. Solving for that, 4.95 meters per second. Multiply that by the cross-sectional area, and we get a volumetric flow rate of 0.476 cubic meters per second. Now, this situation is going to change over time because as the liquid level decreases, as the head falls, the driving force is going to be decreasing. And so that flow rate is going to be going down, and it'll slow down as the 2 elevations get closer together. So it's a declining rate in the same way that for an orifice equation, as the liquid level decreases, then so does the velocity of the jet out of an orifice. You know, if you've got a tall tank like this, when it's totally full, the water's spraying out, but then when it falls, it's sort of trickling with less of a stream because the velocity is lower. All right, any questions about the energy equation or this example? Here's another one where instead of an unknown flow rate, we're interested to find out how much head loss is there between the 2 points. So still, water is flowing from tank 1 to tank 2. In this case, it's a little bit like the pipe rack in the lab. In the lab, remember, we had taps, and you plugged in the differential pressure meter to the taps, and you found out how much pressure loss is there between the 2 points. Here we have pressure difference of 25 psi measured a distance 145 feet apart. So we had our reservoir connected to another reservoir, and at two locations, 1 and 2, and water always flows from 1 to 2. If you've got a pipe and you're not sure which way the water's going, just draw the number 1 and then the number 2 on the pipe, and then instantly the water will be flowing from 1 to 2. Just because you did that, it'll change flow directions even. It's amazing. So here water is going from 1 to 2, and the two locations, L is 145 feet. That's the distance between them. And then the pressure difference, the delta P, is 25 psi. All right, so we want to know what is the head loss between the 2 points. So let's put that into the energy equation and see what we get. In traditional units, the unit weight of water, gamma, is 62.4 pounds of force per cubic foot. And then the other thing that we need to make note of is that this delta P that we're given in terms of pounds per square inch, it's 25 pounds per inch squared, but we also need to multiply that by 144 square inches per square foot. So the change in pressure is 3,600 pounds per square foot. Okay, now the energy equation. We've got P1 divided by gamma plus alpha V1 squared divided by 2G plus Z1 plus H sub P equals P2 divided by gamma plus alpha V2 squared divided by 2G plus Z2 plus HT plus HL. All right. V1 and V2 are the same in this pipe. It's not that they're zero, but because the pipe has the same diameter at location 1 and location 2, the velocity isn't changing. And so we can cancel this term out since V1 equals V2. So V1 equals V2. And that allows us to just cancel it out from the formula. Also, since it's a horizontal pipe, Z1 is equal to Z2. So we cancel that term from the energy equation also. Now here's a tricky thing. It only matters what's between 1 and 2 when you're trying to account for head loss, energy added by a pump or reduced by a turbine. So there could be a pump here. Even if there's a pump before 1, still we would cancel out the pump term because in this equation it's between 1 and 2. So if you look, here's 1 and here's 2, there's no pump between them, so we still cancel out the pump term. And maybe I've never thought of that before, maybe I'll give you an exam question where I've got a bunch of pumps and turbines in places where it doesn't matter. It'd just be like a distractor, and I try to tempt you to account for them. But in this case, we just cancel out the pump term. There's also no turbine, so we cancel out the turbine term. So what we're left with is that the change in pressure from 1 to 2 is equal to the head loss. So we want to find out how much head loss is there. What is the head loss between the 2 points? And you can calculate the head loss by just knowing the change in pressure. So another way of expressing that is delta P divided by gamma will tell us the head loss. And we know that head loss should be in units of length. So we have 3,600 pounds of force per square foot is the pressure, and then 62.4 pounds of force per cubic foot is the unit weight. So the head loss, energy loss between the 2 points is 57.7 feet. On Tuesday, not of next week, by the way. Don't come next week. I don't want to see you here. Tuesday or Thursday. Let me give you both days off. It's on me. But 2 weeks from, not today, Tuesday, December 2nd, we're going to start graphing energy in the system. And a head loss like this, it being a length, is actually relevant because if we were going to graph the energy between 2 points, then you'd actually measure how much higher is the piezometric water surface rising to at 1 versus 2. And this 57.7, that's the water level would rise in the pipe 57.7 feet less at location 2 than it did at location 1 because of that energy loss. Okay. So any questions about the energy equation in this situation? Let's talk about theory. As water flows through a conduit, a pressurized conduit like this, we can think about the control volume and consider the control surfaces. Remember that a control volume is just some imaginary shape that we're keeping track of what goes in and what goes out. When it was the momentum equation, we were keeping track of momentum going in and out and the forces required to hold the system steady. In continuity, we use control volumes to account for whether there's an accumulation and looking at in versus out and if water levels will rise or fall. But we can actually look at energy moving in and out of a control volume as well. And so here is a depiction of a control volume with an outside surface area, the control surface, indicated here in a dash. And what happens is that the water, as it flows through this control volume, the energy that's associated with that flow movement is moving with it. Forces, pressure times area. Remember from the exam where the pressure on the outside of the control surface that's acting in towards the system was counted as an external force. So if we've got this like element of water and we're just looking at what's happening with this element of water, well, for one thing, the pressure on the outside of this element is pushing on the water in both directions. To the right at 1, but also the water here is pressurized, the water at location 2 is pressurized, and the pressure is pushing to the left at that location. So we can keep track of the forces on it, but as it moves through the system, as it moves through this pipe conduit, then the water is actually performing work. Work is a force that's applied over a distance. So force, which has units of newtons per meter squared, multiplied by, force just has units of newtons, multiplied by a length, which is meters, the work will have units of newton meters. So W dot is the flow of work through this conduit. And if we keep track of the velocity of the water and the cross-sectional area and the density of the liquid, we can keep track of, this is pressure here, but if we keep track of the density of the liquid, then we can know the relationship between the momentum and the flow work. And we can look at the rate of work coming into the control volume at location 1 and exiting the control volume at location 2. And so what are the units of W dot flow work, power or work? Anybody know what the units of W dot are? Let's look at that by multiplying the units together of each of the constituents. Okay, pressure has units of newtons per meter squared. Velocity has units of meters per second. Area has units of square meters. And so this cancels out, that cancels out. So we've got a Newton meter per second. Now what's a Newton? Anybody remember what a Newton is in terms of kilograms? And right, kilogram meter per second squared. Kilogram meter per second. Is it kilogram meter per second squared? I'm just all of a sudden blanking out. Newton, yeah, it's per second squared, right? Yeah. Boy, I'm standing up here and it's like I'm a deer in the headlights all of a sudden. Okay, so kilogram meter per second squared is a newton. Then you multiply it by, so we've expanded out the newtons, multiply it by these meters, and then we've got those seconds. So it is kilograms meter squared per second cubed. Right. Another way of expressing it is that the Newton meter is a joule, and so it's joules per second, and a joule per second is a watt. So units of work is watts. That's the expenditure of energy with the time component there. Joules per second. Now, when we're doing the energy equation, sometimes we will apply it to situations where we've got a reservoir of water, like is depicted here, and hydropower is a really interesting application of trying to compare the work that can be done by fluid that has a certain potential energy and the electricity that can be generated, and we'll have to account for efficiency when we do things like that. Here's a pump which works in much the same way as a turbine. It's converting electrical energy into pressure. And I mentioned before that a pump actually adds energy in a way that you might not necessarily expect. The way that a pump adds energy is not by speeding up the water. You know, like, and the reason why it's counterintuitive is, let's say that you have water coming out and it's going through a pipe and it's just sort of flowing out slowly. If you add a pump to this, then the effect that you'd notice, like what you could actually see when you turn on that pump, is that all of a sudden the water is just spraying out with a really high velocity. And so you might draw the incorrect conclusion that what the pump is doing is it's actually increasing the velocity of the water. That's the direct effect that it has. But actually that's not the direct effect, that's the indirect effect. And the way that I can explain that is, think about just upstream and just downstream of the pump. So if this is location 1 and this is location 2, and consider the energy terms, the three terms in the energy equation. There's P1 over gamma plus Z1 plus V1 squared divided by 2G. That's the energy that there is at 1. And then the energy at 2 is going to be P2 divided by gamma plus Z2 plus V2 squared divided by 2G. All right. So how does the pump add energy? There's three places where energy can go. If they're at the same elevation, if Z1 is equal to Z2, then it can't be that the pump is lifting the water. It's not physically increasing the elevation of the water. And since the diameter of the pipe is the same, continuity equation tells us that the velocity has to be the same. If you had a difference in velocity, then the flow in and the flow out would no longer be in balance. So V1 has to equal V2 because of the continuity equation. So actually, the way that a pump adds energy is by increasing the P. The pressure goes up due to a pump. And so that is the work that's done by a pump, is by increasing the pressure of the fluid. As a cylindrical pump rotates, it's actually accelerating the fluid and increasing the pressure. And then, like how we were saying that what you actually see with your eyes is that now the water is shooting out of the pipe more quickly. It's because of the increased pressure at location 2 compared to what it was before. It's that pressure increase that causes the velocity to go up. So it's a cause and effect relationship. We can apply mass balance principles. You know, what we previously did with mass balance, we can do energy balance in the same way. And we can account for, like, we can look at the energy balance, including like the chemical energy of the fluid, considering its temperature. And you may remember talking about enthalpy when you were in chemistry class. We don't usually have to worry about the temperature of the liquids changing in a system like this. The pump gives off a little bit of heat. The temperature change of water as it goes through a pump is essentially negligible. It's very difficult to measure how much warmer the water is as it flows through a pump. And so we usually don't have to go so far as using this version of the energy equation. This version of the energy equation is saying let's even account for the specific enthalpy of the fluid. More commonly, we'll just use this version of the energy equation that I've already presented to you. And so energy is normally measured in joules or meters of fluid in these terms. Work is measured in terms of a Newton meter is a joule, and so it has the same units there. And then power is when there's a time dependency. That's where the watts come in. When it's looking at the number of joules per second that are being expended, then you can do calculations like how much energy can be, how much electricity can be generated by a turbine, or how much energy is required to pump water from one point to another. So here's the power equation that you'll use when you're doing pump equations. You'll calculate the pump head, then multiply that pump head by the flow rate and the unit weight of the water, or whatever the liquid is that's being pumped, and you can find out the power required in order to pump it. And so let's just take one crack at a problem like that in the 5 minutes that we've got remaining. We've got an upper reservoir with the elevation specified. The lower reservoir elevation is given. So water is flowing through this conduit that's called a penstock. That's just a fancy name for a pipe that connects a reservoir to a powerhouse. And we want to find out how much electricity could be generated in this system if the water that's going through that penstock has a velocity of 7.4 feet per second, and we know the diameter of that pipe. So therefore, we're going to be able to calculate the volumetric flow rate Q. And then we have to account for efficiency, because a generator is not 100% efficient at converting potential energy into electrical energy. There are losses along the way. And so here, let's just assume 70%, and really the point there is to show you, do you multiply, do you divide, how to handle efficiency in the case of electricity being generated. Okay, so the energy equation that we are going to substitute into, P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus HP is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus HL plus HT. Okay. If we let 1 be at the surface of the upper reservoir, then the pressure at 1 will be 0. And the same thing is if location 2 is the water surface at the downstream reservoir, then the pressure at 2 is 0. The velocity at both of those locations will also be 0, since it's a free surface of water rather than a certain location inside the pipe. There is a turbine, but there's no pump, so I'm going to cancel out the pump term. And so what are we left with? We'll substitute in the elevation that's given for Z1. The upper reservoir is 4324.4 feet. And then Z2 is 4191.9 feet. Plus the head loss between the two, 5.4 feet. That's already given. That's how much energy is lost as the water goes through that penstock. It's due to pipe friction. So it's already been calculated separately for us as 5.4 feet. And so now we'll calculate with this what is the head that's available to be extracted from the turbine. So the difference between all of these, the turbine head, H sub T, is 127.1 feet. So this is how much head can be extracted by the turbine and converted into electricity. So that's what we'll use in the power equation. Let's find the volumetric flow rate. It's going to be pi d squared divided by 4 to get the area, and then multiply that by the velocity, 7.4 feet per second. So the flow rate is 71.2 cubic feet per second. I was just applying continuity equation to find Q. So the power equation says it's Q times the unit weight times H sub T. The flow rate is 71.2 cubic feet per second. The unit weight is 62.4 pounds per cubic foot. And then the pump, the turbine head is 127.1 feet. So all of that together is 564,660 foot-pounds per second. We can convert that to horsepower. Power is sometimes expressed in terms of horsepower, where there's 550 foot-pounds per second per horsepower. Okay, so the power that we've just calculated is equivalent to 1026.7 horsepower. But that's if the system was 100% efficient. And I already told you it's 70% efficient. So the question is, do we multiply or divide to find out how much power actually can be harnessed from this system? If you've got 70% efficiency for a turbine like this, we need to multiply by 0.7, and then that'll tell us that the useful power is 718.7 horsepower. Can be utilized for 70% efficiency. Okay, so that's a turbine. If it's a pump, you divide by efficiency rather than multiply. And we'll get a chance to deal with that in some examples. That's it for today. I hope you have a great Thanksgiving. I'll see you on Tuesday, December 2nd. And if you've got any questions on the homework or the water gem stuff that you're working on, just send me an email and I'll do my best to respond.